from CCMB department. Today talk about foundation of algebra and number case studies. Applications of algebra in cryptography, modular arithmetic and group theory. Modular arithmetic is core concept used in many cryptography algorithms. Example in RSA encryption and decryption. They are used in WhatsApp to secure the message for like encryption and decryption. Group theory.
So I think we were discussing in our class like group theory is the area where we come across the concept called modular algorithm, where modulus is the concept, modular addition, modulo multiplication. These are the areas what we come across in group theory. Am I right? We were discussing in the class. So what he says is these concepts, these modular type of concepts can be taken as a case study towards real-time scenario. Like as he said, you can use it in encryption and decryption. Where WhatsApp messaging transferring is very important, very commonly used platform for message transfer. Where these kind of encryption, decryption concepts can be made more secure way, Okay.
Next, group theory. Group theory uses different element key exchange, RSA and elliptic curve cryptography. Group theory is a binary operation satisfying addition and multiplication. There are main conditions are associative, closure, identity and inverse. There are main conditions.
So these are the main conditions what we come across. You know very well. There are four important laws: closure, associative, then finding inverse and identity should be there. So these fundamental ideas of group theory can be directly applied into cryptography, so that it gives a strong, secure transaction. Okay, very good.
Elliptical curve algebra (ECC). It is based on an algebraic structure of elliptical curve over finite fields. In cryptography, the curve may be added using the algebraic functions, and the number of multiplication of the number larger is possible, but the reverse of the number is impossible in the elliptical curve algebra. Next, the finite field or gradual field used in AES, advanced encrypted standard algebraic transformations like subbytes and mixed columns rely on field arithmetic.
So already we were discussing in the class about fields. The fundamental concept of fields comes from sets. So when a set is connected with one binary operation, it gets connected with groups with certain laws. Again, that certain laws of group with two binary operations, it is getting connected with rings. We call it as rings. It's the next level of group theory. So again, field is the next level of fields where we have, that is the next level of rings, where suppose if there is a ring with the commutative concept satisfied, with commutative inverse identity and unity exists. So these conditions are getting connected with the ring theory. You can connect with field. Field is the next level updations of these scenarios, and field is the area where these kind of research is happening with cryptography. All those things are getting connected with fields. So already there are different types of fields. What we study in our class is exactly connected here, because we are talking about finite field. In our class, I think you all know, we are talking about Z7, Z8, Z9, Z10. So N is finite field what we are discussing in the class. The same scenario is trying to connect with cryptography. Very good.
Matrix algebra helps perform transformations and mixing operation to obscure the input data. Polynomial arithmetic used in error correction codes, stream ciphers and block ciphers.
Good, very good. So like ring theory, there are various other aspects of algebra, like as I said, matrix algebra is there. Matrix algebra is a kind of grid nature, with rows and columns with the numerical mathematical operations involved in it. Again, those areas are, I think we are talking about permutations, we are talking about matrix, 2 cross 2 matrix, 3 cross 3 matrix, like kind. Even in groups, you can bring matrix inside and you can see whether it is satisfying all the laws of the groups. So such kind, even groups can connect with matrix and you can exactly connect with the applications. So as he rightly said, so we can connect various areas of algebra with the concept of cryptography, not only cryptography, in various fields of Internet of Things. where various things, various remote sensing is happening. So in those areas we can have a secure connection between the objects. So as he said, apart from normal algebraic identities, we can use various law related concepts of algebra that still lot of researches are going, where we are using how strong the key can be. Key is nothing but the security code, whatever, how strong it can be made so that the hackers cannot break it. So such kind of areas are going now. There are lot of researches are going into it. Maybe you all can be interested towards that, and you can connect more of algebra into the real-time blockchain analysis. Okay, so that is a updated level. We can move mathematics more into this kind of approaches. So, like he said, there are different types of analysis. Again, recently we were talking about polynomials. So, how the two polynomials can be divided, so that we can find the quotient and the remainder. That remainder concepts again we are trying to connect with field. So, field, different types of modular fields we take. In that we take various polynomials and we can divide those things, and we understand how the remainders are got, what kind of quotients we are getting. So again we saw about certain theorems also. We saw factor theorem, remainder theorem. These theorems are mathematical approaches which is connected with problem connections, and again those things can be applied with real-time problems. So as they mentioned, mathematics of algebra and number theory can be entirely can be applied into blockchain analysis. Okay, so thank you for listening.